Okay, so let's talk about it. What kind of process can we talk about? Process. And one thing that is for sure is isothermal. I want to know when things are isothermal. What that means your delta T is 0, right? What about the other one? That's right. Adiabatic. And what is my cheating note on Adiabatic?
Q is equal to 0.
That's right. That's something that I can do. But what about the isothermal itself is not well defined. I also wanted to know about whether things are reversible or irreversible. And then this one is a P external, right? Is constant, right? And when the external process, this table is meant to be for finalizing the delta S scenario. And for calculating delta S, when external pressure is non-zero, it's not easy to calculate. So I will just put external pressure is 0. That makes our calculation easy, and we got actually one equation. So this one is especially we're talking about when external pressure is 0. When external pressure is 0, do you know what your work irreversible here? Zero, right? So we are talking about reversible. You're changing volume 1 to volume 5, volume 2. Same thing here. Volume initial, volume final. We are talking about, I think the expansion is something that easy to visualize. And compression is just a different sign, different direction for this. So let's think about reversible expansion, irreversible expansion. And then what do we say about the delta S? This one, right? We are in business actually. This is initial temperature is final temperature is the same. And we just call it a T. I like that. That's another way to say delta T. Do we know about Q reversible? I'm interested in delta S here. And also I'm interested in delta S total and delta S around it. I want to know these three quantities here. But I need some starting point. So Q reversible. Do I know this value? It's a reversible, right? Q reversible, isothermal. Isothermal volume change Q reversible. Looks like we have done this one. Remember this? What was our original equation? This Q reversible, work reversible together supposed to be delta U. Remember now, right? What is this situation? Isothermal?
Q is equal to 0. Q is equal to
Is 0, right? Delta T is 0. Delta U is 0. Well, we are talking about ideal gas. Okay? We're not talking about complex one. This is an ideal gas. So I guess this is also ideal gas. So this one we know from the chapter 2 or first law of thermodynamics. Do you know this? Which is essentially Q reversible is minus work reversible. Yeah, you know we already need. And if you remember, reversible isothermal expansion work was minus nRT volume final volume initial. That's the work, right? And then you need a negative sign, so this one becomes positive. Well, can you tell me what's your S now? What is your S? Which is we call Q reversible minus T. And somebody,
and
N R.
N R times the natural
Natural
log
log,
of VF over VI.
There you go. You got your delta S. At least I know how one mathematical form. When there is a volume change, keeping the temperature constant, the delta S for that kind of a reversible isothermal expansion, that is what I know. Okay. What about my delta S surrounding? I think I have to write that one. Delta S surrounding is T surrounding Q surrounding. So that's an equation. But do I know Q surrounding? I don't think I really easily know. But there is one thing that I know. That's why this equation I like it better. Combined with this one, delta S total is delta S plus delta S surrounding. All right. So instead of calculating this, I want to do the backdoor. What's my delta total?
0.
Because
Reversible.
reversible. Okay? So therefore, and then using the equation shown that this one is a S plus S surrounding, right? So that must be a minus delta S. Okay? That's how we do it. And so therefore, if you need an equation, that will be minus NR natural log Bn. So I'm in physics. So to think about the adiabatic, I already know. I mean, that was an easy freebie, right? Because of the reversible adiabatic, reversible delta is total is 0. I can jump onto that. And because of this one is essentially reversible heat. Right? That's right. I mean, this one is T initial and T final. They are not the same. And you calculate in your exam that what's my final temperature and calculate other quantities based on this. Different temperature during adiabatic expansion is a key. But regardless, if it is a reversible adiabatic, because of the reversible heat is defined by 0, what's my delta S? Whatever the temperature it is. Temperature is actually third law of thermodynamics is temperature cannot be 0. That's the third law of thermodynamics. And this is always positive. Okay. So what is that? 0 divided by something. There you go. You got this too. So what am I have? Delta S is 0. What's my delta S surrounding? I mean, I'll probably want to write here. What's my delta S surrounding?
0.
Yeah. So this is the most easiest case. When things are reversible and adiabatic, this is all 0. And whereas this is probably the most commonly frequent equation. This is a very kind of well noted equation. We'll come back to this kind of equation, deriving it using what is called the Maxwell relationship. Probably next week we're going to do that. But this one itself, from what you guys already know, I can do that. Okay, I can get this. This is not the favorite method, but we can do this. Okay, so let's do this. The reversible total. So one thing that I always try to get a shortcut. What's my delta S total? I don't know the value. I just know it is bigger than 0. Right? That one is true. Delta S total This is bigger than 0. So this is true, but in this case, I will have an exact equation like this. The delta is total mean. This one is actually the most challenging. So here's another one that I think that I wanted to think about. So let's think about it. Reversible expansion that is isothermal, irreversible, right? But we look at the scenario. I'm at the initial temperature and initial volume to final temperature, final volume, and temperature in and out, initial and final. And I mean, this is the same statement. What we called an isothermal process, right? And that was a reversible process. So I know reversible process, I can use this equation that I already know, and I can calculate that. And this is the equation that I got. But do you remember S is state function? What matters is a state difference between before and after. Okay? And the thermodynamic variable, such as an S, should depend only on temperature and the volume. And this case is not so different. It's exactly the same, right? We know same volume, same final pressure, whether reversible or irreversible, same temperature before and after. So their state is the same. So what I can say now is, since S is a state function, delta S is same as delta S reversible isothermal. Because I'm just looking at the state before and after, which is the same as the one shown up here. So therefore, I'm just going to borrow what I know already. So that's a sort of the one of the leaps that you have to have. This is an important concept because of the initial volume, final volume. Volume is defined, temperature is defined. So it's a one state to the other, and so therefore I can change it. So keeping the temperature constant, I'm gonna let this go. And the volume change, whether it's a reversible or irreversible, I can calculate the delta S. And when it's a reversible, now it allows me to use this equation, right? Delta S is Q reversible over P. So I can calculate that. The other one, I don't have an equation because I don't know what's my reversible Q. But I can steal this equation from what has been derived for the reversible combined with the fact that S is a state function. Okay? So what's then the delta S surrounding? This is a little tricky. Okay? So delta S surrounding, which is an isothermal, and this is a Q surrounding, and this is a T surrounding. Okay, this one this one actually can be used. So remember, this one I cannot really drive anything, but because external pressure is 0. What makes that happen was your irreversible work is 0. Am I right? Okay. And then we also know delta U is 0. We know that, right? Because it's isothermal, right? So delta U is 0 because delta T is 0. So what's my Q irreversible in here? For this case,
0.
is 0, right? This is a value that I cannot use to calculate my delta S system, but delta Q irreversible is 0. And when delta Q is irreversible, what this textbook explained that this is your system, this is your surrounding, right? I'm making on purposely big, this is your surrounding. And what they're saying is heat Q irreversible, process irreversible, and that's 0, right? And from the perspective of thermodynamics, surrounding is essentially everything else besides a system, so it is a huge, okay? So therefore this Q irreversible from here, as far as the surrounding is concerned, if I change my perspective from system to surrounding, Q the irreversible or Q surrounding is 0 here. Because that's surrounding reversible. So whether this is a irreversible process, from the surrounding perspective, they can essentially, there's no change in the surrounding. Okay? But that's a kind of philosophical statement. The surrounding is so big, whether the things that irreversible change, as far as the surrounding is concerned, they essentially maintain the same. So this one translates into, as far as the surrounding is concerned, it is done in the reversible and there is nothing else. So then I can use this and finally come up to an answer that delta S is 0.